All right, well, I'd like to thank everybody for joining us today. My name is Greg Wadley, and I'm with CTC and Associates. I'm the Clear Roads Program Manager. We're all here today to view the final deliverable, which is a webinar for one of our fiscal year 2013 projects. Each project, as they're completed, is required to present a webinar as a final closeout deliverable. And this project is for understanding the effectiveness of non-chloride liquid agricultural byproducts and solid complex chloride mineral products. The principal investigator for this project is Laura Fay, and she's out of the Western Transportation Institute at Montana State University. One of the standard practices for us now here with Clear Roads in our final webinars is to mute all lines. And because of that, we're going to ask that if you have any questions or comments, to please go ahead and use the chat box. That way, the principal investigator and everybody else can see what's being asked, and we can address those either throughout the, well, actually at the end of the webinar. Obviously, we will not be addressing those things throughout the webinar, but at the end. With that being said, I'm going to go ahead and turn it over to Laura, and we'll go ahead and kick off the webinar.
Great. Thank you, Greg. Thank you, everyone, for calling in. I appreciate your interest in this topic. So the title for the webinar today is Understanding the Effectiveness of Non-Chloride Liquid Agricultural Byproducts and Solid Complex Mineral Products. And this is a large undertaking by many, many people from many different organizations, including Mr. Ambu Muthumani, myself, Laura Fay, at the Western Transportation Institute, the original PI on the project, Dr. Shanming Shi, who's now at Washington State University, and then Mr. Dave Bergner at Monte Vista Associates. We'd really quickly just like to thank everyone, including the Clear Roads Pool Fund and the member states for funding the project, as well as the Minnesota DOT for coordinating the project. Even bigger thank you goes out to the Technical Advisory Committee, which are Clear Roads members. Folks are listed here. They were really instrumental in helping to kind of direct and steer this research project. And I'd also like to say a huge thank you to Colleen Boss and Greg Wadley at CTC and Associates for their coordination. And then another huge thank you goes out to the WTI support staff, and this includes all of the lab techs that help with this research, as well as the communication and editing staff. So to introduce this topic, complex chloride minerals, or CCM products, which is how we refer to them in the final report, and agro-based products are increasingly used in snow and ice control operations. Now, these products can be used alone, such as a rock salt, or more commonly, they're being used as additives. So this would be maybe a beet juice added to a salt brine. Now, past studies have shown that these products improve de-icing or anti-icing performance, reduce corrosion rates, as well as reduce environmental impacts. But the modes of action by which these agro-based byproducts provide benefits is fairly poorly understood at this point in time. Before I get into the objectives, one thing I'd like to state is that for this project, a lot of the information that was found has been initially conducted by manufacturers or vendors in order to assess how well these products work. And so less information was actually found by third-party researchers, and you'll see that in the report and in the literature review section. So the objectives of this project were to conduct a literature review, conduct a national survey, as well as a systematic laboratory investigation. Now, the laboratory investigation was used to assess the chemical and physical processes by which the complex chloride mineral-based products and agro-based products are of value to winter maintenance. So we assessed a whole suite of different characteristics, including how these products work to lower the freezing point of water, how they are used to improve the ice melting capacity, how they work to weaken the ice bond to the pavement, as well as how they work to reduce corrosiveness to metals and infrastructure, while at the same time improving longevity of the product on the pavement surface, as well as preventing ice formation or refreezing on the pavement, and assessing the influence of UV light or the absorbance of sunlight and how these products work. In order to convey this information, we created the final report and presentation, which you're seeing now, but a part of that was the development of a best practices manual, which I believe is chapter 5 of the final report, and that's basically a summary of all the findings. And then the final deliverable, which is in the final editing stage, is a video, which is being created by the MLT group, who created past ClearRose videos, and it's a summary of the major findings, and that eventually will be available on the website as well. So to get into the literature review, so some of the main results include that the main composition of agro-based products include desugared beet molasses, corn byproducts, cheese brewing byproducts, beer brewing byproducts, succinate salts, urea, and starch. Now these products are either used alone or as additives with other winter maintenance chemicals, as mentioned previously, so it can be used as, say, a rock salt or as a beet juice added to a salt brine. And the goal is that they can improve performance and reduce corrosion and environmental impacts. And a newer group is the liquid deicers, which feature these blended chlorides as well as maybe an additional mineral component, so a complex combination of chlorides. Now, recent studies have shown that improved performance from agro-based products and naturally occurring chlorides occurs for snow and ice control operations. And additionally, studies have shown that the use of these products leads to reduced risk to highway infrastructure in the environment. But at this time, there's still limited research that's been performed to identify or investigate the modes of action by which these products help in improving performance and reducing the negative impact to infrastructure and the environment, further supporting the need for this research. As previously mentioned, we conducted a national survey. For the survey, we received 31 responses from 16 states, which are highlighted in gray in the upper right corner. A general summary of the information captured from the survey includes that some respondents prefer using non-chloride agro-based products at lower temperatures, so below 20 degrees Fahrenheit. And that longevity on the road surface or the residual effect of these products was one of the observed benefits of using agro-based products. Additionally, improved performance at low temperatures and reduced material usage were common benefits stated by survey respondents for the complex chloride mineral-based products. So those would be like a rock salt-based product. But again, even from the survey and the literature review, limited research was conducted or identified by survey respondents on agro-based products and complex chloride mineral-based products. So getting into kind of the meat of the project, which included the laboratory testing, we used the literature search as well as the survey to identify a whole suite of different complex chloride mineral-based products as well as ag-based products. The following 10 products were selected and broken out into 3 categories. So here we have category A, which is solid complex chloride mineral-based products, which are tested as received from the vendor or manufacturer, and we have products A1 and A2 listed there. Category B products are liquid agro-based deicers, which were prepared by mixing the vendor-provided concentrates with a salt brine solution, and they were mixed at either a 70-30 or 80-20 by volume ratio, and this mixing ratio was determined based on vendor specifications. We did not make it up. We consulted with them to determine the optimum blending ratio. And you can see the 4 category B products that were used. And the category C products, which are the liquid agro-based deicers, these were used as received from the manufacturer, so there was no diluting or mixing of these products. And you can see the 4 category C products that were used for testing here. So what we're going to go through now are all the various tests. Oh wait, really quickly, I'm going to jump back. So here's a big summary table of the different products. So the top two here, this is category A products. So these are the complex chloride mineral-based products. You can see the major components, how they were used, essentially where the information source is in the percent chloride. The information captured for this table was either received from the vendor manufacturer or the MSDS sheets. And as you can see for some of these products, the information was not provided due to proprietary protection. So here, if you jump down, you can see the 4 category B products here. And as you can see, here's the blending ratio for the salt brine that was mixed with these products and then the major components. And then the category C products here, you can see that they were used as received and what their major components are. Now what's interesting to note is here we actually measured chloride content of all of these just as a baseline. And for reagent grade sodium chloride, there's a theoretical chloride content of 60.07 or 60.7%. And for the complex chloride mineral-based products, you can see that they had very high chloride concentrations. So that's in line. Now for the category B products here, the percent chloride measured should be close to 3.99 if it's a 23.3% brine solution. And these were mixed with salt brine, but the molar chloride concentration was measured prior to them being mixed with the salt brine solution. So this is the chloride concentration of the as-received samples from the vendor before they were mixed with salt brine. And these are the samples that were received from the vendor and used as is, not mixed. And here's the molar chloride concentration. So jumping into the lab testing, we wanted to look at how these products lower the freezing point of water. And essentially we captured information and created eutectic curves for each of these products. Here's a schematic of how the system was set up. Here's what some of the data looks like as it comes out of the system, and here's what some of the beakers look like as you're reaching your freezing point. And then here's an example in the bottom right of what a typical eutectic curve looks like for salt. So to get into the data, here are the eutectic curves of the products tested. We have the category A products, or the complex chloride mineral-based products, and then the reagent grade salt. And you can see here that it's right in line with the eutectic temperature of about -5, -6 degrees. For the category B products, again, you have the different products, and then you have the salt brine control and the dotted red lines. And what's interesting, as you can see here, you have your reagent grade salt, and you have your -5, -6 degree eutectic temperature. But for all of the agro-based products that were mixed with salt brine, their eutectic temperatures are way below salt brine alone. So that's an important thing to note here. For the category C products, again, we have the salt brine control and then all the products that were tested. And all of the as-received agro-based products, they did not freeze below -45 degrees Fahrenheit. So again, they have a very, very low, very cold eutectic temperature. So to summarize the findings of this, for complex chloride mineral-based products, they do not significantly reduce the freezing point of water compared to salt alone, and they did not produce more ice melt than salt. And we'll look at some ice melt data next. For the liquid agro-based products blended with salt brine, so these are the category B products, they did significantly lower the freezing point of water compared to salt for the salt control. And for the agro-based products as received, or those category C products, they significantly lowered the freezing point of water compared to salt brine, and they produced more ice melt than salt brine. And one thing that we'll discuss further is that these agro-based byproducts seem to be acting as freezing point depressants, and this may be because they might be cryoprotected. And we'll get into this more later in the discussion. So as mentioned, we also looked at the ice melting capacity of these products. What you can see here is the Petri dishes with ice lens in them, and then the product applied on top of that. So you can see some of these products, especially the ag-based products, had a much darker color, and they're easier to see than some of the other products. We used a syringe to extract the amount of ice melt over time, And these are all in a cold chamber where we can drop the temperature as cold as we want, control humidity, control the UV exposure, and make snow. So for ice melting capacity, here is our data. So at 25 degrees Fahrenheit and 15 degrees Fahrenheit, we measured the ice melting capacity for all the products every 10 minutes, or, well, up for an hour, essentially. And what you can see here is that for the Category A product, they consistently increase their ice melting capacity over time, with ice melting occurring at a great rate up to an hour after. And the same is true at 15 degrees Fahrenheit. To a lesser extent, you can see the y-axis here, but there's still significant melt occurring at 60 minutes. And one thing that we would recommend for future testing is to see how far out this goes. How far out do you get this continued melting of these complex chloride mineral products before they stop working? This could potentially influence when you put products down, how long you leave them out, and then when you actually return to plow. If these products are still working well, well after an hour, you may want to wait on how long you might want to delay your plowing a certain amount of time based on how much functionality you want to get out of the product you put on the road. And then if you jump down to the two middle figures, we have the Category B products. These are the agro-based products mixed with salt brine. And you can see here at 25 degrees and 15 degrees, we're not getting a ton of ice melting. Now remember, these products had significantly lower eutectic temperatures than salt brine, but we're not getting as much ice melting. And that's where that cryoprotectant theory comes in, is that maybe they're not melting a lot of ice, but maybe they're preventing ice formation from occurring. And then if you jump down to Category C products at 25 and 15 degrees, you can see here you are getting ice melting over time, not as significant as the complex chloride mineral-based products, but you do see ice melting occurring up to an hour after application, even at 15 degrees. So looking at all these results, I'm going to jump all the way out here to the right-hand side of this large figure. So we have ice melting results after 60 minutes. So the total milliliters of ice melted per gram of material, or per milliliter of liquid material applied. So at 25 degrees, we have the ice melting. At 15 degrees, we have ice melting. And then for a select few, we did ice melting at 5 degrees. And what you can see here is that at warmer temperatures, you get more ice melt consistently across the board. At colder temperatures, you're getting less ice melt. And then at 5 degrees, regardless of product type, almost all the ice melting rates or ice melting capacity is about the same. And that's kind of important, especially when you're talking about complex chloride mineral-based products only working to a certain temperature. Let's see, what else can we talk about here? Again, here's the eutectic temperatures that we discussed. And then in the context of the characteristic temperature, so this data here was collected using the DSC, and essentially this is the temperature at which ice formation will start. And what you can basically see is that these are relative numbers, and for the complex chloride mineral-based products, what you can see is that ice formation will start to occur at about 28 degrees. And then for the Category B products, these are the agro-based products that are mixed with salt brine. And so your ice formation is starting to occur just kind of below where the complex chloride mineral-based products occurred. And that makes sense because a large component of these products is salt brine. Whereas the Category C products, these are the manufacturer-created products that frequently don't have as much salt brine in them. And you can see that they have a much lower point at which the ice formation will start to occur. So what's all this data mean? Well, for complex chloride mineral-based products, they produce more ice melt than salt brine alone, or the salt brine control, at about 15 degrees Fahrenheit. And for the liquid agro-based products that are blended with salt brine, the Category C, or excuse me, the Category B products, they actually did not produce more ice melt than salt brine. And this is an interesting finding, especially when you compare it to the lower eutectic temperatures. But the agro-based products as received, or the category C products, they did produce more ice melt than the salt brine. So there's some difference between the manufacturer-produced products and then the agro-based products that you then blend with salt brine. There's some difference going on here. But generally speaking, the agro-based products exhibit significantly lower characteristic temperatures. So that's that eutectic data that we looked at. And this suggests that the amount of thermal energy corresponding to the aqueous brine solution's liquid-solid phase transition is reduced by the addition of the agro-based products, making the agro-based byproducts mixed with salt brine more difficult to freeze than salt brine alone. And that's really where this theory of the cryoprotectant comes in, is that maybe these agro-based products actually prevent or halt the ice nucleation from occurring, and therefore prevent the ice bond from forming. So another test that we did was we looked at how these products weaken ice bond to pavement. This was a really neat test that was designed. So we have these pavement samples here on the left that were made, and then we created a grid where the different products were applied. You can see here with a pipette. Now this person is in the cold chamber, so it's 25 degrees, it's 15 degrees, or it's 5 degrees, so it's very cold. We used snow that was made in-house and sieved for uniformity. It was applied and then compressed onto the pavement sample down here. You can see here some of the liquid anti-icer bleeding through the snow. And then the pavement sample with the compacted snow was trafficked using this tire, and it was trafficked 250, 500, and 750 passes. And this test method was used to measure the amount of shear strength or shear force that was required to remove this 2-inch by 2-inch section of snow and ice that was bonded to the pavement. So here's the data. So what we're looking at is the pavement sample and the product applied, and the amount of force that was required to remove that section of bonded snow and ice from the pavement. So as you would expect, the pavement sample with no de-icer, it required a lot of shear force or shear strength to remove that pavement or the snow from the pavement. Here's a rock salt control, and then the category A products. These are the complex chloride mineral-based products. They generally performed really well or on par with the rock salt, essentially lowering the amount of shear strength necessary to remove that snow and ice from the pavement. Category B products, so these are the agro-based products that were mixed with salt brine. They all performed really well. They all had very low shear strength that was required to remove the bonded snow and ice from the pavement. So these are good anti-icers. Better than the salt brine and way better than the asphalt with no de-icer on it. And the category C products down here, these were the as-received agro-based products. And again, they all performed really well as anti-icers, having really low shear strength that was required to remove that snow and ice from the pavement. As previously mentioned, a subset of the samples was then used for additional testing to try and tease out some of the mechanisms behind what was going on and why these products work. So salt brine was used as a control, and then products B4, C1, and C4 were used. And ice melting, the ice melting test was conducted for these products as well, as you may remember, at 5 degrees. So basically at 5 degrees and 15 degrees Fahrenheit, you can see here the difference in the shear strength required. Basically what's interesting here is that at 5 degrees, for some of these products, less shear strength was required to remove the product. But also note that these whisker marks, these black air bars, that's the variation between all the different samples that were run. So each pavement sample for each product type had 6 replicates run. And so this data is a combination of the 6 replicates. So it was repeated for multiple pavement samples for multiple replicates. And you can see here that the error bars are pretty significant. But as a general trend, you can see that for some of these products, they actually function really well at low temperatures as anti-icers. One of the interesting things that came up as we were doing this testing was the fact that, these agro-based products are really good anti-icers. So they weaken or prevent that ice bond to the pavement compared to salt brine alone. And why might that be true? And some early research suggested that maybe viscosity had something to do with it. So as an add-on to this project, we actually measured viscosity for those 3 products. So product B4, C1, and C4. And remember, product B4 is an ag-based product that's mixed with salt brine. So it has a pretty low viscosity. But products C1 and C4 were as received from the manufacturer, and they had higher, and then for C1, much higher viscosities. And so we were thinking that maybe viscosity had something to do with this in terms of weakening that bond, or at least function as a better anti-icer. So for kind of summarizing this data, for complex chloride mineral-based products, bond strength between the ice and the pavement was slightly reduced compared to salt brine at the temperatures tested. And for the agro-based products, and this includes category B and category C products, so ag-based products mixed with salt brine, and then the agro-based products as received from the vendor manufacturer. The bond strength between the ice and the pavement compared to salt brine was significantly reduced at all temperatures for all products. And the addition of the agro-based products to the salt brine, so the category B products, increased the overall viscosity of the products compared to salt brine alone. And the agro-based products with the higher viscosity than salt brine may actually have a slower grain boundary penetration than the salt brine with the lower viscosity. And I don't know if you remember from the picture we showed previously, but you could see some of the anti-icer bleeding through. And essentially what happens is the snow wicks up some of the liquid off the pavement. And what we're theorizing is that the more viscous or the thicker the product, the less will be sucked up into the snowpack. And so essentially it will be left on the pavement to actually work as an anti-icer. So to further investigate this, we looked at how these products improve longevity on the pavement. And this was mentioned as one of the benefits of the agro-based products from the survey respondents. So we used those same test methods where we had the pavement sample, we applied the product, we compacted the snow on top of it, and then we trafficked it for 250, 500, and 750 passes. And then we measured the bonds, or the shear strength that are required to move that patch of snow or plow that snow off the pavement for these 4 products. But we did it at colder temperatures. We did it at 15 and 5 degrees Fahrenheit. And what you can see is that for the 15 degree, there's a slight trend where you see it requires slightly more and more strength over time to remove the snow off the pavement. At 5 degrees, it's kind of all over the map. There's a slight trend for some of them that it requires more strength, but for others, it's just kind of uniform. And that at 5 degrees Fahrenheit, it requires a little bit more strength. So to flip this component of the lab testing on the other side, we wanted to see, we measured the shear strength to say, how much plowing force does it take to remove the snow and ice for the various products. But we wanted to look at the snow that was left. And from that snow, how much product was actually up in the snowpack instead of on the pavement surface. So we collected the snow that was plowed, and we measured for the B4 product, we measured the chloride concentration. Because again, remember, this agro-based product is mixed with salt brine. And what you can see here is that at 15 and 5 degrees Fahrenheit, after 250 passes, 80 to 90% and 45 to 80% of the salt brine associated with that product was removed in that initial plowing. So a lot of the de-icer or anti-icer was wicked up into that snowpack. And then by 500 and 750 passes, the amount of product that was wicked up into the snowpack significantly dropped down to 5 to 10%, as you can see. So for the agro-based products mixed with salt brine, what you can see here is that after about 250 passes, the bulk, at least half at 15 degrees and up to 90% at 5 degrees, the bulk of this product is whipped up into the snowpack and removed with plowing. And only a tiny fraction, 5 to 10%, actually remains on the pavement surface. Now for the category C products, so C1 and C4, we did the same thing, but the major constituents of these products are not chloride, so we couldn't measure the chloride concentration to determine this. So we used the UV spectra, and we basically identified the characteristic peaks for these different products, and you can see those here. And what you can see is in purple, we have at 250 passes, at red 500, and at green we have 750 passes. And again, you can see the same trend that you saw with the chloride-based or ag-based product that was mixed with salt brine. You can see that by 250 passes, the bulk of the product is removed with plowing of the snow, and that only a small fraction remains after at 500 and 1,000 passes for these. So that may actually be a typo. I need to go back and double check that. So to summarize, for the agro-based products that were tested, and these are just the B4, C1, and C4 products, they tend to stay on the road surface longer than salt brine alone, and that the longevity of the products on the road surface depends on the amount of product that is dissolved into the snow or wicked up into the snow before each plowing cycle. And for agro-based products, they tend to wick less into the snow when compared to salt brine, and this may have to do with the viscosity of these products. So we also wanted to look at how these products prevent ice formation or refreezing, and this was actually measured using the friction coefficient. So we used a similar method to prepare the samples. We put the product on the asphalt, we made the snow, we compacted it, and then we trafficked it. And while this looks very similar to the shear force or shear strength, it's actually measuring friction. And we'll just get into the data. So what we have here is two figures, and we have friction coefficient on the y-axis and the number of passes on the x-axis and the different product types. And what you can see here is that at 250 passes, you have a pretty high friction coefficient that steadily decreases with time. So the roads are getting more and more slippery with time at 15 degrees. And there's a similar trend, but a less pronounced trend at 5 degrees. Basically, the roads are just slightly more slippery at 5 degrees in general. So to summarize this data, the agro-based products tend to have better friction values during the extremely cold snow events and during the repeated warm snow events. And the agro-based products act as ice crystal nucleation point inhibitors, delaying the formation of ice formation compared to salt brine. Now, these are the cryoprotectants I was talking about earlier, which are substances that prevent ice nucleation from occurring. And the agro-based products significantly reduce the freezing point of water, therefore could act as these cryoprotectants, delaying the freezing point of water while not necessarily having a higher ice melting capacity. Another aspect of the lab testing that we looked into was the influence of UV light. So we looked at the absorbance of sunlight, not only if it impacts the product in terms of degrading it, but also does it influence the product if it's darker? Does it melt more product? Here you can see this is the ice melting test again in the cold chamber. And you can see there's an ice lens with some product put on top of it. And then we expose these samples to what you would typically see in the wintertime in a northern snowy climate. So we're thinking like Idaho, Montana type of sun exposure. And here's the data. So for these 3 products and the salt brine control, we measured ice melt at 15 and 5 degrees. And one major thing that you can see from this data is that regardless of product type, UV light adds to melting capacity. It significantly increases it. So we also measured the ice melting capacity with no lights on and no UV exposure. And you can see here that there is ice melting occurring, but the ice melting rates are much lower than with the direct UV exposure. So in summary, for complex chloride mineral-based products, higher intensity sunlight, which is the direct UV exposure, the ice melting capacity was similar regardless of the product type. One interesting thing that we found with this test, it was the first time we had ever done it, and that even though the environmental chamber had a very tight temperature control, the location of the sample placement was influenced by, well, the sample that was directly under the UV light had more melt than if it was on the outside of the exposure to the light. So we basically shifted all the samples multiple times and collected data multiple times so that hopefully to even out this exposure. But what we realized was that we could categorize the ice melting rates of these by high intensity exposure and then medium intensity exposure. And so that's kind of what we're getting at here. So that for the complex chloride mineral-based product, the medium intensity sunlight, the ice melting capacity was slightly higher than for salt, the salt control. While for agro-based products with the higher intensity sunlight, the ice melting capacity was similar regardless of product type, regardless of temperature. And one of the interesting findings that we were hoping to tease out of this was that at the colder temperatures, the darker colored agro-based products had higher ice melting capacities than the lighter agro-based products. And that likely has to do with the albedo factor, and that darker products will absorb more light than the lighter ones. This test, as I mentioned, was the first time we had conducted this. We highly recommend that someone uses this data as a starting point and runs with it. We feel that a lot could be learned from this data set in terms of how much product is put out there and how effective it is, whether you put it out during the day or the night, and when you need it to function, and how well you need it to function, especially at northern and very southern latitudes. This could really influence how your product is working. Now, we also looked at the corrosion rates of these various products. Another interesting thing identified in the literature review in the survey was that the agro-based products reduce corrosion rates. So we used the PNS dip test, which you can see here. And then here's an example of the 3 triplicate or replicates that are dipped into the product. And then here you can see these washers. This is a washer with no corrosion. And the percent corrosion rate is actually a calculated value compared to salt brine. And then this is a 30 to 40% exposure, 70 to 80%, and then a 90 to 100% corrosion rate exposure. And we also measured electrochemical corrosion rates to compare the two. So what did we find? Well, now again, remember, this is all relative to the corrosion rate of salt brine. So you can see here that the percent corrosion rate for the PNS dip test for salt brine is normalized at 100%. And so you would hope that all the products would have a lower corrosion rate than the salt brine. And again, these products were tested at a 3% concentration, and that's just the standard practice for these tests. So when you compare them to the salt brine, the complex chloride mineral-based products had lower corrosion scores, which is great, but they're still pretty high. For the agro-based products that were mixed with salt brine, for most of these products, you can see that they had significantly lower corrosion scores, though one did have a higher corrosion score and may just need additional testing. And for the Azure Seed manufacturer created agro-based products, again, they all had significantly lower corrosion scores than salt brine. So there is some truth to the fact that people say that these agro-based products have lower impact on infrastructure. And the electrochemical data, or the average corrosion rate, which was calculated, falls in line with these. So here's the salt brine control, and you can see here that all the products, with the exception of a few, they're a little high, have much lower corrosion scores. So in general, the PNS dip test, which was that test where you dip those 3 washers in, revealed that the complex chloride mineral deicers do have a slightly lower corrosion score than the salt brine control. And most agro-based deicers in category B and category C have much lower corrosion to carbon steel than the sodium chloride controls, with the exception of one product, and that just may need to be retested. So we're going to shift gears here. All of the information just presented was on all the lab work that we just completed. And then one of the tasks that was mentioned was to take this information and create a best practices manual. So what we did was we summarized the findings of the lab results, and we included that in the best practices manual. Other components of the best practices manual included information on storage guidelines, material handling and loading, storage and mixing, brine production equipment, application methods and guidelines, anti-icing and direct liquid application, and then also identified issues with agro-based products. And I'm just going to quickly summarize what's in the manual. So for material handling and loading, one of the important things that was identified was that for loading solid products, those complex chloride mineral-based products, often they're loaded with buckets that are too large, and this leads to loss of material. So one recommendation is that folks use a smaller bucket. It may require a longer loading time because more buckets are required to fill the back of the truck, but it reduces loss of material on site. And then also loading equipment should have a way to track these quantities. And some equipment does, but some doesn't. And I think for a lot of folks, it's just upgrading to newer equipment or tracking systems so that you know if you're losing material, if you know that people are sticking to application rates, and then you know how much you have on site, you know how much is going out, you know how much is getting put down on the road. For storage and mixing, especially for the agro-based products, use blending ratios that work. For our lab testing, we used the blending ratios for the ag-based products that were recommended by the vendors. Now, the vendors, they sell you the product that's going to work at its peak performance. And so when they suggest a blending ratio, they do it for a reason. So if you're going to modify a blending ratio, you should have a really good reason for doing that. And if you do modify a blending ratio, you need to track it, you need to study it, you need to see what worked and what didn't work. And I actually suggest if you do start modifying blending ratios, put it out on the Snow and Ice listserv or put it out to the Clear Roads group and say, hey, we're trying this. It worked, it didn't work, here's what we do next time. I think a lot of folks could learn a lot from that kind of information. Additionally, blending solid materials, whether it's, well, I guess in this instance it would be pre-wetting. It's not recommended to do it on the apron. It's really not accurate and it's not very efficient. Instead, use a metered supply line to blend at the pile or on the truck. And here you can see a truck is metering out the blending rate, and then they'll move the solid material, pre-wet solid material inside or load it in the truck. For solid storage guidelines, solid material should be stored on an impervious surface and covered. And I'm just going to keep hammering this to folks. I know you've been hearing it for a long time. Almost everyone's doing it. Some people are trying to move towards it, and it's very important. Storage facilities should be designed to accommodate typical runoff in your area. They should provide sufficient space for indoor loading and unloading, and consider prevailing wind direction to limit snowdrift and precipitation indoors. The picture on the bottom right was captured from PennDOT and the Penn Turnpike, and basically they have what they call the 10-foot rule, and that even though they have their products stored on an impermeable surface in a covered storage container, they don't have it the fourth wall walled off, and so they place the building appropriately to limit snow drifting, but they always store the product 10 feet back, and that allows that product to stay dry and clean, and it also allows some room for the vehicles to go in and capture that material. Storage areas should be routinely inspected and maintained, kept clean and orderly and well labeled, and this is just general information that applies across the board to everything. For liquid storage, all liquids should have secondary containment, and double-walled tanks are great, but they will not protect if a hose or a fitting breaks. And so even if you have double-walled tanks, you should have secondary containment that can capture all that lost material, and it should be outside of where those fittings and hoses are. If you have indoor tanks, have a berm at your ground level door to prevent loss of material out of the door. And I also recommend consulting with local environmental regulators regarding siting of liquid storage tanks and containment requirements. They may not have any, but they may actually have some great recommendations. And it also shows due diligence. If a spill does occur, you can say, well, we did consult with them, and this is the plan that we came up with. To avoid spills, we recommend routine inspections. And if something is found, maintenance should be performed. And spills should be captured, cleaned up, and disposed of as soon as possible. One thing that came up with secondary containment was that a lot of folks have a water release valve, because if your tanks are outside, if it snows or rains, that liquid will build up in that secondary containment. And so they will just essentially release the water out of a drain. But if you forget to close that drain at night and your tank breaks, then you're just going to release all that material and your secondary containment is useless. So have a check system in place to make sure that that valve gets shut after you're done draining out the excess water. Application methods and guidelines. Generally, we recommend pre-wetting or slurry and high ratio pre-wetting, anti-icing, or direct liquid application. All these practices reduce the loss of material to bounce and scatter. It keeps the product on the road longer, and the product activates quicker. And then some issues that have been identified with agro-based products, which generally can be dealt with, but may have hindered some folks from using them thus far. Road slickness has been reported in some cases, but road slickness has also been reported for just some chloride-based products. And in a lot of those instances, the product was over-applied. So regardless of what product type you're using, make sure that you're not over-applying that product, and that can help reduce road slickness. Clogging of spray equipment has also been noted as an issue. And to avoid this, we recommend flushing your system with water between use of various products, and then agitating or stirring it periodically if you're storing the product for long periods of time. So that would be if you have product left over at the end of the winter and you're going to store it all summer, maybe before you use it that next winter, give it a nice stir and maybe test it at your shed. Bacterial growth has also been noted. You know, these are ag-based products, so bacteria could potentially eat off of the sugars. And so some products do have inhibitors in them to prevent this. But some vendors and manufacturers actually report a shelf life for these products. So if you're buying a product and they say it's not going to work after a year, write that on the container. And then at the end of the year, if it's up and you still have some left, test it. See if it works on site. If it does, great. If it doesn't, then you'll need to dispose of it. But proper long-term storage for excess material would be no sun exposure to avoid that helping bacterial growth, cool temperatures, so in the shade or inside, and then with periodic mixing. And then anecdotal evidence has suggested that these products may attract wildlife to the roads, but we already know that salts alone attract wildlife, and there's no research yet that shows that ag-based products added to salt attract more wildlife. We definitely recommend additional research in this area, but at this point in time, there's not enough information to conclusively say one way or the other. So with all of that information being presented, I wanted to say thank you, and I will open up the floor to questions at this time. I'm going to get the chat box opened up. I think there's a few questions already. Okay, from Clay Adams. He asked, regarding the corrosion testing, we noted that one of the ag-based samples had a higher corrosion score, and we suggested retesting. At this point in time, we don't have planned to do additional corrosion testing. We actually tested each sample more than triplicate, but it may be a factor of the batch that we received. So what we actually recommend is when you order products, get third-party testing on them, or go to the qualified product list on the PNS website and see what their values are and compare it to yours. If you don't have in-house corrosion testing, there are some places around the country that can do that for you. But generally speaking, agro-based products had much lower corrosion than salt brine or rock salt alone.
Thanks, Laura. Is there anybody else out there that has any questions? If so, please go ahead and type them into the chat box, please. Okay, looks like we got another one from Clay.
Okay, so I'm going to go way back here. Oops. Okay. Bear with me, folks. Clay Adams asked, could you go back to one of the first charts and explain the molar concentration difference between the solid and the liquids? Yes, I can. Let me find that chart. Here it is. Okay. Yeah. Collapse this box. Okay. So initially, to determine a baseline for all the products, the 10 products that we were testing, we wanted to figure out what the chloride concentration was. For the reagent grade, or sorry, for the solid products, when you measure chloride, theoretically you could have up to 60.7% using the molar concentration or Moore's chemical titration method, and these chloride concentrations were very high. For the agro-based products that were mixed with salt brine, the category D products here, you can see that the molar concentration of chloride is relatively low, and for some of these products they do have some sodium chloride added, but the bulk of the sodium chloride was added after the chloride was measured. So essentially we're just measuring the chloride concentration of the agro-based product that's then mixed with the salt brine. And for the category C products received from the vendor, you have the molar concentration here, and you can see for some of these they have a much higher molar concentration. Again, for some of these, due to proprietary protection, the concentration of the various components was unknown. This test method is not fault-proof. There are some elements that are present that can interfere with the test method. It's not 100% accurate, but this is what we were able to report from the testing that we conducted. I hope that answers your question, Clay.
And we've got a question from Ron Wright.
So Ron asks, in the table that shows the molarity of the chloride, do you plan on representing that the chloride content was in the virgin inhibitor? If by virgin inhibitor you mean the product that was originally shipped, yes. In the final report, we have a footnote for this table that says that the chloride concentration measured here is from the virgin material that was received from the manufacturer. All right, Clay says thanks. Any other questions from anyone? While we're waiting to see if anyone else has any more questions, I'd just like to say for the technical advisory committee for this project, we're working on getting that final draft or final editorial review of that video ready. I will be in touch with you this week with a date when you guys can view the video to provide comments, and then do a final review of that so that it's ready for posting on the website.
And we got one from Cliff Spoonmore.
Okay. It says, iSlicer claims they are effective to -32, but your results prove that it's not. So one of the things we struggled with in this project is to use product names or not. I'm going to move forward. So let's see. iSlicer is product A1, and here's our eutectic curve. So what we see here is the eutectic temperature of product A1 is on track with all the other complex chloride salts, which is -5 to -6 degrees Fahrenheit. Now, with that being said, we also found that the ice melting capacity for these products continued, even at 15 degrees, past an hour. And that's really where I recommend that additional testing is, while these products may not have the lowest eutectic temperature, they seem to work for long periods of time. And knowing how long that product can work is very important.
Okay, anybody else? Laura, do you want us to unmute people just to sort of open it up a little bit so that people can more freely ask questions or provide comments just for a little bit?
Yeah, I'm fine with that.
Okay. All right, everyone, you are unmuted. So if you would like to unmute yourselves on your own end, if you are, and then you're welcome to go ahead and ask questions verbally instead of to the chat box. But there is another question by Clay in the chat box.
It says, Clay asks, what % solution of iSlicer did you test? For the ice melting test, it's applied directly as is. So the grains are sieved so that they're uniform and then applied. For the for the corrosion testing, they're all tested at 3%. So it's uniform across the board. For the eutectic, I'm going to have Ambu. Ambu did the eutectic testing. Is he on the line still?
Sure, yeah. Let me go to that slide, actually.
Clay just wants to know what concentration the iSlicer was tested for the eutectic curve.
So basically how this eutectic curve created is we take, you see the solution concentration, the slide number is 12, I think. Laura, can you go to that number from your side?
There you go.
Yeah, thank you. So if you see the solution concentration, so that tells how much is the solution concentration by weight. So let's say, for example, we take 10% of by weight of iSlicer, and then we allow it to freeze and find when it freezes. So that is the data point there. Then you take 15%, then you take 20%, and it goes on like that. So what happens is at one point, the concentration is so high that it will start to freeze earlier. So there is no like fixed concentration. It is tested at different concentrations. So hope that answers the question.
Hey, Laura, this is Ron Wright. In this, did you guys, I can't recall, did you guys have an effective temperature range that you helped establish using the DSC?
Yeah,
I couldn't.
So here's the chart with the DSC data. And you can see here the characteristic temperature peak for the different products. as compared to the eutectic data and then the ice melting data. So in terms of bracketing an effective temperature range, we did not do that for this product, or this project. But we did characterize the characteristic temperature using the DSC, the eutectic temperature, and then the ice melting capacity at various temperatures for each product.
Laura, this is Scott Lucas here with Ohio. One thing I was kind of curious about, and I've seen this a lot in the eutectic temperature on the phase shifts and that, when you start getting over that 23% solution of material, you have the refreeze rate in that. And I was just curious about that. In the field environment, how easy is that to obtain? Or is that something that is something that should be of concern to the actual workers out there? Or is this more just like a lab-induced type of response, or what are we looking at?
So I brought up the eutectic curves. This is just my feeling, and I'll let maybe some other folks like Ambu and Ron and the guys out in the field talk. But you know, these are lab results. These are ideal condition results. And what you're going to see with a lot of these products is you may apply them at your ideal concentration, but then they're going to be diluted. So to me, what's really important here is your ideal applied concentration, and then what's going to happen as they dilute. So as the solution concentration gets lower, and you see that a lot of the products still perform, their performance just reduces with time. But with that said, maybe I'll open the floor to Ambu or Ron to comment on that.
I guess to further cover that also is the only thing I was curious about with that, I mean, Ron or somebody to cover this as well. A lot of people have the practice of constantly salting bridge decks. I mean, we've kind of taught that many times in the past to make sure you have that, or interchanges. I know guys that have that common practice of doing that, and where we're creating more issues than we're helping in those cases. And I know anybody saw anything like that in the field reality, or if it's once again just a lab thing.
Were you saying oversalting interchanges in bridge decks? Let me see.
Scott, are you talking about the effect that since a bridge deck is in the air, you don't have any heat left in the Earth's surface coming up to it, and so since it's wrapped top to bottom in cold air, you're using more salt on a bridge deck to reduce the ice? Is that what you're getting at?
I think he's maybe muted. I'm not sure.
Sorry, yeah, I was muted. Actually, you're seeing a situation where you're actually having so much salt on the bridge, you're actually getting above that 23% concentration. You're getting like to 30% or 35 or whatever it may be. And I don't know if it's even possible to do that, but then you're getting to where you're going to be, your solution is going to be freezing at a much higher temperature than normal.
Correct.
Right.
And you are correct there. If you over apply the salt, it could be 15 degrees outside if you've got a wet pavement, and you'll just start making salt crystals on the deck, because it will turn into a crystal.
And that's it kind of quote unquote freezing, is when it just crystallizes. Kind of like what you have around a brine maker, when you got that the seep of it coming out of the fittings and that, you have crystallization of salt. Is that what we're looking at, that kind of a reaction?
No, it's, well, what you're doing there is you're going up the right-hand side of the eutectic curve.
Correct.
And looking
right.
at the increase, the temperature's coming up, and you're starting to move out of the ice and solution phase into, you've got a saturated material coming on there, and it's actually crystallizing and turning into a solid salt.
Okay.
So the more that you put on there, if you look at the sodium chloride, the higher the concentration goes, That's why it kind of dies off when it gets up around 26%. If you look at the chloride curve at 26%, something like that, you quit because you got rock salt at that point.
It's just salt, and there's no water to do anything with that. Or, yeah.
Well, there might be a little bit of water tied into it, but you're talking, you know, around 24 degrees at 36% or 26% sodium chloride, you got a salt crystal.
Okay.
And I don't know, Laura, if you've got a eutectic curve phase in there that's labeled with all the bisects for water, solution, ice, and solid, and the solid being the chemical phase, being turned from a liquid to a solid. I mean, you get crystallization of ice, but as you keep going up, you can actually form the solid material with ice in it. But it depends on the temperature.
Right.
Yeah.
We didn't make one, but you can see one here on the bottom right hand of the screen of the standard for salt eutectic curve, where you get too much salt, you get refreezing, too little salt, you get refreezing, and there's this magic area. The hard part is keeping that magic area on your pavement.
Okay. Thanks a lot. I appreciate it.
All right, any other questions? Okay, hearing none, I just want to let you know that I did get a question from Tom Peters asking if when we were going to have the webinar up on the website, and I do believe that our goal for that is early to mid next week. So keep an eye out for that. And if there are no other questions, then I'll just go ahead and thank Laura so much for your presentation today, and to the rest of the Clear Roads group and others who were able to join us as well. Thank you very much.